In this lesson, we'll examine Bohr's work quantitatively. So there's an assumption coming into this lesson that you understand what a spectrum is, and you understand that when we give energy to atoms, light is produced, which produces these different spectral lines, which are connected to the amount of energy that's given off from the electronic transitions that occur. And what we're going to do now is we're going to look at the calculations that Bohr did that allowed him to predict the wavelength of the spectral lines for certain transitions in a hydrogen atom. We'll just briefly talk about Rydberg. So Rydberg was studying the spectrum as well, and he was studying it experimentally rather than using specific calculations, which we'll see that Bohr did. And he developed a relationship very similar to Bohr's that was able to predict wavelengths for the spectral lines produced in a hydrogen atom or a one electron system. We're going to focus on Bohr, and he developed his own equation based on his principles of the model of the atom. And basically what he did was he developed an equation that described the energy of an electron in an atom based on physical constants such as the mass of the electron, the charge, Planck's constant, and also an integer, which he called the quantum number. A quantum number, and we're going to look at the principal quantum number, which is identified by its value of n. And what n is, if you think about a Bohr atom, it is the energy shell that an electron can be found in. So when we talk about an energy level of 1, that's the first energy level closest to the nucleus, that would have a value of n of 1, or the principal quantum number for an electron in that shell is 1. And so on and so forth. If the electron is in the second shell, then it would have a value of n is equal to 2. So his equation looked like this. E is equal to negative b over n squared. And b is the combined constant that takes into account those factors which I mentioned before. And it has a value of 2.18 times 10 to the negative 18 joules. It's sometimes also reported in electron volts. 1 electron volt is 1.6 times 10 to the negative 19 joules. And so these two, Bohr's constant in electron volts is 13.8. Okay, we're going to work in joules. So what we're going to do before we start plugging into this is we're just going to look a little bit more into this formula to understand especially why it has a negative. So when we look at the energy levels in a hydrogen atom, we know that as we move away from the nucleus, the energy gets higher. The amount of energy of that given electron gets higher. But when we're looking at Bohr's equation of E is equal to negative b over n squared, okay, we have a negative value for our energy. And that's based on the fact that we can't really measure the energy absolutely. So while we are thinking about it as having a formula to know the amount of energy of an electron at this moment in time, we can't actually measure it absolutely. So what we had to do is assign a free electron, so an electron that's not part of an atom, to have a value of 0. So if you can imagine our 0 point is here and our nucleus is here in the atom, and as we go from a free electron, which is not attracted to the nucleus at all, to an electron that's on the first energy level that is closest to the nucleus, this is the amount of energy that is assigned to that. Okay, so negative b over n squared would give us this magnitude of energy, and it's going to have a negative value. You'll see then for the second energy level, where it's negative b over n squared, okay, there's going to be a smaller amount of energy. And you'll also see that it's not equidistant, like the amount of energy between 1 and 2 the difference between those is not equal to the amount of energy between the second and third energy level. And that's because of that quadratic portion of the formula. So oftentimes when we draw a Bohr representation of an atom, we try to make it look perfect and we try to have all of the rings, the same distance from each other. But in this model here, you can see the relative distance a little bit more accurately. Okay? So the difference between 1 and 2 is bigger than the difference between 2 and 3. And as we move farther and farther away, the difference in energy between the shells gets smaller and smaller and smaller. And the value we're assigning to the energy is going to be negative. So it's going to be negative relative to the amount of distance. Basically, you want to think about it as a magnitude that's related to the distance that the electron needed to go from being a free electron to being attached to the nucleus. So it's going to have a larger magnitude when it is closer to the nucleus, okay? And a smaller magnitude when it's farther from the nucleus. Okay, so what we're going to do next is we'll actually calculate the value for different levels. So, because ultimately what we want to be able to do if an electron is undergoing a transition, it is going to fall from a higher energy level to a lower energy level, and we want to calculate the amount of energy associated with that. I'm going to do an example with the n is equal to 2 just to get us started because the 1 is a little bit boring. Okay, so E is equal to negative b over n squared. So negative b will be negative 2.18 times 10 to the negative 18 joules. And if n is equal to 2, we're going to divide by 2 squared. We're going to divide by 4. So the value here is negative 5.45 times 10 to the negative 19. Okay. So that energy here, negative 5.45 times 10 to the negative 19. And my joules is written up there. So when I take this same constant, it's the same for all the energy levels, and I sub in different values for n. The values that I get for n is equal to 1, I get negative 2.18 times 10 to the negative 18. Oops, I don't need to put joules. And you'll see this magnitude, this number, the magnitude of it is larger than this one, just like we saw a moment ago. Okay, so for 6.06 times 10 to the negative 20, and for 10, it's negative 2.18 times 10 to the negative 20 joules. Okay. So essentially what we want to do, if we want to figure out the amount of the wavelength of the light that's being emitted when an electron undergoes a particular transition, what we need to do is find the difference in the energy between the levels that it fell from and to. So what we're going to be doing is using Bohr's theory, and the difference in energy that we're going to find is the higher minus the lower. Okay, so we're going to find that difference in energy. And this is a little bit unusual from our experience in the past with finding the delta of something. A lot of the times people will just automatically say it's final minus initial. And so this requires a little bit of a side explanation. So I'm just going to help us to make sense of the fact that why are we subtracting the lower from the higher, or the initial from the final instead of the other way around. And it comes back to that fact that what we're doing here is we're assigning an electron that is free to have an energy of 0, which is not actually true. The energy of the electron is actually quite high. We just don't measure that energy specifically. We're looking at it relatively speaking. So if we look at this a transition here, and we're going from, if you look at this electron, it is starting at the 4th energy level, and it is going to the 3rd energy level. And what I've done here is I've made some fake numbers so that we can kind of see relatively speaking. But what we're interested in is we're interested in this red difference here. We want to know the difference in the energy of these two. So it's not 4 minus 3. It's not the difference in the principal quantum number, because that's not the energy. Remember, energy is calculated using E is equal to negative B over n squared. And so these values aren't true, but I want to work with simpler integers so that you can kind of see the point here. So if this electron here, so you can see with this arrow, I'm starting at my free electron. It's coming closer to the nucleus. So when it comes to the 3rd energy level, there's this amount of energy associated with that. And on the 4th level, there's this amount of energy. And just visually, you can see that this magnitude is going to need to be larger. So I gave it a value of -6, okay? But it is going to be negative, just like this formula assigns. And my EH is -4, okay? It's a little bit smaller. So if I did the final minus the initial, -6 minus -4, I would end up with an amount of energy that is -2. And that doesn't make sense. We don't have negative energy. What we're looking for is the difference between these two. And so what we want to do is we want to take the higher one, -4, and we're going to subtract the energy of the electron at the lower level, -6, and you can see there we get the +2. And that's really what we're looking for. We're just looking for that energy difference between those two shells. When Bohr did his calculations, he developed these different series, and what you'll learn to see is that some of the electronic transitions that occur in hydrogen are visible to us, which is what leads to the spectrum being produced, but there are also lots of transitions that are not visible. So in these series here, you see they're showing examples of electrons falling to the 1st level. These are referred to as the Lyman series. The Balmer series are electrons falling to the 2nd energy level, and then there's the Paschen falling to the 3rd, and the bracket falling to the 4th. This isn't something you need to memorize, but it is common that you do see it, and it does give you a good sense of visually what is the amount of energy associated with transitions that we are able to see, and how does it compare to transitions that we're not able to see. Because one of the things that you'll be asked to do is you'll be asked often, can we see this particular electronic transition in the visible spectrum? Or what is the type of light that's being produced, whether it's UV or IR, based on the wavelength that you have. So what we're going to do is one example, and we've already looked at and determined some of the data that we need for this. So we want to calculate the wavelength of a spectral line produced in the hydrogen spectrum when the electron falls from the 6th orbit to the 2nd orbit. Okay? So this is going to be part of the Balmer series, and we're asked if the line is visible. Okay? So we have our data from above. We already know the amount of energy of the light in the 6th orbit and the 2nd orbit, and we're going to find the amount of energy, therefore, that's released by the difference between those. So we're going to do first delta E is equal to E of the higher minus E of the lower. So in this case, the higher is the 6th, and the lower is the second. So we're going to take our values from our previous calculations. We have negative 6.06 times 10 to the negative 20 joules. We want to be careful to manage our negatives carefully here. We're going to subtract negative 5.45 times 10 to the negative 19 joules. And we are left with 4.84 times 10 to the negative 19 joules. It's important that we use our calculator properly using the scientific notation, and we pay careful attention. We're expecting a positive number, so if we end up with a negative number, we want to review our work and make sure that we haven't made a mistake. Now, this is the energy associated with that electronic transition, but what we want to do is we want to determine the wavelength of that light so that we can see, is it red light, is it purple light, is it blue light? And so we want to remember our formulas from before, and we have a formula that is E is equal to HC divided by lambda. So if we rearrange this formula, we have lambda is equal to HC over E. So lambda, so H and C are also constants. So it's our Planck's constant, 6.626 times 10 to the negative 34. Joule seconds. The speed of light is 3.00 times 10 to the 8 meters per second. And our energy, 4.84 times 10 to the 19 joules. Okay, so being very careful to do our calculation properly. We get 4.10 times 10 to the negative 7 as the numerical value. Looking at the units, our seconds simplify, our joules simplify, and so this answer is in meters. Now, to figure out if we can see this, what we need to do is look at it in nanometers, because that's what our electromagnetic spectrum is shown in. And to go from meters to nanometers, you want to divide by 1 times 10 to the negative 9. Okay, so you're left with 410 nanometers. And this is in the visible spectrum. Okay, it is between the visible spectrums between 400 and 700. Remembering that violet is on this end. Okay, so we expect that to be violet. And if we look back at our Balmer series here, we can see in this example, the electron that's gone from the 6th level to the 2nd level is our violet light. Okay, so we can go all the way back. These red, green, blue, and violet, you can see those are connected to the spectrum of hydrogen. Okay, this one here is it. Oh, that's showing red. So this is our hydrogen spectrum. We can see this is the spectral line that we were studying there. So that spectral line resulted from an electron falling from the 6th orbit to the 2nd orbit. And what Bohr was able to do was do with calculations that determination.